Let's start.
Do it.
Let's do it. Let's first set some expectations. I'd like for today, tomorrow, and the other day, which is Wednesday, Thursday, Friday, it's more of like to relax and have just understand the concept and have fun about it. And I'd like to use more of the time for you guys to catch up, and please grab me like after the lecture if you don't understand anything or you need help with whatever you need help with. Okay. And again, the algorithms are very important, but in your case, to be frank, I don't think they would ask you already because you already got they won't interview you technical questions, I think, in your case. Yeah, but still, it's still good. Okay, so my format will be, I show you some slides, I show you some visualizations, and then I may or may not even show you the code because I feel like it's unnecessary at this point. Okay, so without further ado, I guess let's start with the code for the day. Algorithms were used by programmers when they do not want to explain what they did. Yeah, so you can just say a mumbo jumbo random stuff if you don't want them to understand what you're doing. Don't know where it is. Okay, so let's move on with the slides. So the topic for today is searching and sorting. But before that, we should talk about algorithms. Okay. First things first, as humans, when let's say they ask you to find a number, usually you would see all the numbers, let's say in the board, right? Or in a sign or somewhere, and you can easily spot, hey, there's my number 2. Hey, there's number 50 that I want, right? However, though, for computers, they can't see the whole picture right away. They need to do a step-by-step to check a number. So focus on the step-by-step. Okay, they either have to go randomly check it. Again, it's one by one. They can go from start to finish, still one by one. Or they can do some operations to divide and conquer, but still it's step by step. Okay? So algorithms, in a very easy explanation, is a step-by-step instructions for completing a task. Let's say waking up early in the morning. Set your alarm, turn it off, and then the alarm goes on, and then you turn it off again, and then you wake up. Let's say completing a task, doing some shower. You just go inside the shower, open the shower head, rinse some water, and then that's done. And usually a good example is, let's say, recipe to cooking. Okay. Again, algorithms are the building blocks of computer programs. They are as important to programming as recipes are to cooking. Okay, that's the very main analogy that you always have to think about. They're like just recipes. Here are the set of instructions. You have to do this, do this, do that, do this, and then complete. Okay? An algorithm is a well-defined procedure that takes an input and produces an output. Okay? It basically means that if I want to search for something, I should either get a Boolean value that, hey, I found it, or let's say I want to search for something and let me know where is that index, and then return that index, which is a number, again, an output. Okay? The main difference here is that algorithms are mathematical or textual in nature. So you can go down the rabbit hole of studying algorithms and be very good at making your code efficient and keep on refactoring it. So next question is, how do we know an algorithm is efficient? First, we do check the computational complexity. Okay. Computational complexity, it allows us to analyze an algorithm if it's efficient or not. How? We'll check if it can scale as we throw larger and larger data sets at it. Let's say you have an algorithm to find a number, but you only have an array of length 10. But what if you have an array of length 1 billion? Is it still efficient? So the data set scaled, can your algorithm scale as well? Okay. Most of the time when we talk about computational complexity, we talk about big O with the O notation, and that denotes the worst case scenario. An example of worst case scenario is, let's say you have a linear search for an array and you have 1 billion elements. The worst case scenario is the number that you want to find is at the end. So that's 1 billion steps. Okay? On the other hand, omega, best case scenario, but we usually don't really use that a lot for explaining our space and time complexity, is omega. That is the best case scenario. Let's say in 1 billion elements, the number is at position 0. So that's so fast, right? Computational complexity, we rank them from fast to slow. O of 1 meaning any number, it's constant. I'll show you a graph later. Logarithmic is just a reverse of exponent. Linear is when you say O of n, it's times n the number of elements. So let's say O of 1 billion elements. Okay. N log n is, let's say, the length of the array times the log n, meaning the reverse exponent of result of n. Quadratic is anything, let's say 1 billion, and you square it up. So 1 billion times 1 billion. Polynomial is you multiply your base number with a constant. Exponential is very dangerous come to this point because you now times the constant with the number of elements. And factorial, as you all know, is if you have a number, you multiply all the preceding numbers, 5 times 4 times 3 times 2 times 1. And infinite, that's Buzz Lightyear. Yeah. So in computational complexity, we always talk about two stuff. One is the time, which is execution time. The other one is space, or memory consumed. So if you have a for loop, and it would ask you how long does it take. So you can have some API to check how long is your for loop running. And also you can do it by scratch or by hand to just check how many loops did you do, like a counter. Say you loop for 10 times, right? Another thing is space or memory consumed. Some of the harder algorithms is when they ask, okay, let's say you have to make sure that everything is still in place, meaning you don't create a new array, because creating a new array creates an extra memory, right? So sometimes they want to just swap elements within the array. It makes it harder, okay? Also, this is where you do the trade-offs. As programmers, as problem solvers, we always have this pros and cons. So let's say you want to go for more efficiency, but it takes more space. But again, we can say that we maybe can do more space because right now the hardware for memory is inexpensive, right? Or let's say you want to use more space so that it's faster. Okay. Next, algorithms to analyze effectiveness, they use the big O for time and space complexity analysis. Same one. Measures the worst case complexity of an algorithm. Again, that's big O. And here's a graph. So if you can see this one, this is the constant time. This is types element, and as you have more data input, it's still constant. It will still run, let's say, if it's 5 seconds, it's going to be 5 seconds. However, for your O of n first, this one is the easiest one. So it means that if your array gets bigger, the time it takes gets bigger as well. This one, with the log n, again, it's just the reverse of exponent, meaning as time, your data size increases, the shorter the time it takes to finish, because you keep dividing stuff. Let's say an example of log n is, let's say you have 500 elements, okay? In O of n, you go from 1, 2, 3 until 50. But in log n, what you do is you have 50. The next time it searches, you divide it by 2. That's 1. And you divide it by 2 again. Let's say it's 12. That's 2. Divided by 2, 6, 3, and let's say 2 or 1. 5 steps compared to 50 steps. Again, this one is squared, and this one is called a cube. Qubit. And end of n, that's pretty bad. Yeah, pretty bad. So if you have, again, 1 billion, it multiplies by 1 billion. And this is the same thing. This is a cheat sheet in the internet, very popular. So green, the dark green means excellent. This one. Most of the time, you can't really get to this point when you do where you do for the time complexity. However, it's kind of common as well for space, memory consume, complexity to have just, access time, sorry. Access time to have constant time. Because some data structures like hash table, they're created very efficiently in such a way that when you want a key value, you get it very fast. Instead of like for array, you want a value, it needs to do search one by one. Okay? So O of n is still okay. Most of the time, we're fine with n log n. Because most of the time, you have to sort some stuff first. And then now you do the algorithm of, let's say, divide and conquer.
There's no faster sorting.
Yeah. So as you can see, here, we don't want this. Okay? And just to give an example for, let's say, O of n, and let's say O n raised to 2. This one is, let's say, you have one for loop. This is, let's say, you have a nested for loop. If you nest it more, so 3 for loops, you would go here. Okay. Again, this is elements. A while ago, we showed that the downside, the x-axis is your data input, and your y-axis is time. And as well as this one is the number of operations, steps, and number of elements, which is the data input. Okay. Again, just to emphasize, even though we always say that it's time, we don't really measure the algorithm itself by time. We measure it by how many steps it would take. Okay. Okay, so we'll talk about some fundamental algorithms, searching and sorting. Okay, searching is just basically iterating over the data structure's element to retrieve a data. Okay, an example, let's say you have a bookshelf and you have to go check them one by one. Okay, you can either go from this to this or the other way around, but basically you do it one at a time until you get the right book, grab it, and then that's how you access it. Pretty easy. Going through each element of the array, one index after another sequentially. So that's your linear search. And again, the time complexity is O of n. Okay, the length of the array. Next, we go for binary search. So a good analogy for binary search is, let's say, Yellow Pages or phone book. So most of the time, if you're looking for something, you open it up in the middle first. If it's not there, let's say you're looking for, let's say the word Clark. You open in the middle, and you found, let's say, M. You kind of know that you don't need to get the after the M, which is the right. You know that you need to flip on the left, which is before the M. You keep doing that until you find C and Clark. Okay. Okay. Binary search can check the middle value to see whether the desired value is greater or smaller than it. So in binary search, we always start at the middle of the array. And if we see the number right away, return it. If not, go to the left or go to the right. If it's not there, go to the left, go to the right. Okay, so how do we go left or right? So if the desired value, go ahead.
Does this only work in sort of?
Yep, correct. So how do you know if it's left or right? So if the desired value is smaller, this algorithm can check through the smaller parts. Let's say because it's sorted, the left side is smaller, you go check at the left. Or it can search through the bigger parts if the desired value is bigger, the right side. Okay? The time complexity of this is log n. And again, log n, just think about is reverse of exponent. And then you divide things by 2. Okay, 100 divided by 2, 50, 50 divided by 2, 25, and so on. And you have lesser steps. Sorting. Basically, you put data structures, elements in order. Again, searching is just looking for something. Looking for something. Sorting is rearranging stuff. Okay? And you may want to put them in your terms of order, maybe ascending, descending, or other stuff. Okay? One of the common sorting mechanism we have is bubble sort. Like a bubble, it bubbles up. Okay? What it does is it simply iterates over the entire array and swaps the element if one is bigger than the other. So what happens is, I'll show a visualization later, but let's try this. Let's say I'm position 0, and I check my position 1. Am I bigger than you? If yes, let's swap. If not, I stay. I look at position 1 and check again. And let's say position 1 is bigger than position 2. Now I swap with position 2. At position 2, I check position 3. Am I bigger? Yes, I swap again. Am I bigger? I swap again. So it bubbles up until you go to the end of the array, and now that's sorted. That specific position is sorted. You don't have to go through that again. So the time it takes, the number of steps, is O of n squared. Okay? And the space, again, now we're talking about space because this is sorting. Searching, we don't really need to have space because we're just looking around. Okay? The space for this one is just O of 1. It's cheap. Next is we have selection sort. Selection sorts works by scanning the elements for the smallest element and inserting it into the current position of the array. So what it does is it searches for the array. Let's say the first loop. Let's say I want the maximum. I'll check all of the elements, tag 1 as the maximum value. Let's say at position 3, I have 100 as the maximum. I put it at the end of the array. Okay, next loop, I check the remaining elements. Check again, what's the maximum? Tag it at, let's say 95 was the maximum for that iteration. I grab that and put that next to the end of the array. Again, you can also do this selection sort the other way around by looking for the minimum and let's say putting it at the beginning of the array. Okay, time it takes is the same as a bubble sort, n squared, and space is of 1. Insertion sort works similarly to selection sort by searching the array sequentially and moving unsorted items in a sorted sublist on the left side of the array. Okay? I guess it will just confuse people more. Let's wait for the visualization for this. Time is of n squared, space of 1. Quicksort works by obtaining a pivot, partitioning the array around it, bigger elements on one side, smaller elements on the other side, until everything is sorted. On average is n log n. Worst case is n squared. Space is log n. It's bigger than O of 1. Merge sort is a very popular sorting mechanism as well. It works by, let's say you have an array, and you divide the array into 2 arrays, and you divide the 2 arrays and it becomes 4 until you get a subarray that has a length of 1 each. So it's like you keep slicing the array until you have an array length of 1 for each of them, and now you keep comparing and merge them again. Okay, so first you divide the array, and then once everything is divided to length of 1 of array, length of 1 of array, length of 1 of array, now you can compare and merge them. It becomes a length of 2 of array, another length of 2 of array, another length of 2 of array, and then now you can compare again and merge them. It becomes length of 4 array, length of 4 array, and then combine, and it should have the same length as the original. So if your original length of the array is 8, it should go back to the length of 8 once you merge everything. So time on average is n log n, and space is O of n. Okay, let's just show you some visualization. I think we have the sorting. Let's zoom out. Searching first, sorry. So let's have this array of elements. Let's say we want to search for 227, or which is in position 9. So in this GUI, we can just put 227 and do linear search. So as you can see, every time it goes through an element, it evaluates. Is it equal to 227? No. Next. Is it equal to 227? No. And then at position 9, is it equal to 227? Yes. And then again, it's up to you. You can either return that you found it, it's true, or you just return the position. Hey, it's in position 9. Okay, let's try another number. Let's say 1,000. Do we have 1,000 here though? No. Keep going, keep going. And then again, let's say you search for the value of 1,000 and it is not there. And you can either return, let's say, false, you did not see it, or you can either return -1 to denote that I didn't find it, or you can just return null. Okay, there's a bunch of ways to tell the user that you didn't find it. Again, even though it did not find it, the algorithm itself is correct. Okay, the algorithm did not fail. It's just that the input, there's no target. The target, you can't find the target yet. Let's do binary search. Let's say we want 199, which is in position 8. Click binary search. That's way too fast. Okay, let's do it again. Again, what it does is first it grabs position 0 and position 31. It uses that as the whole length, okay? Now it checks the middle. It always checks the middle. If it's less than, if let's say the target value, it's 199. The first time it goes around is, it sees, let's say, number 15, right? And it sees that, hey, the current value is greater than the target, which is 199. So if you have that, please change my length to be 0 to 15 and check the middle again. Okay, let's try to run that one more time. You see the red box, it checks the middle. Red box, red box, red box, red box. So one thing to note about is, even though after a few iterations, let's say you shorten the search, and it starts with 199, but it still doesn't see the 199. It has to keep going down until it becomes the middle. Okay. Okay, we can move on with that, and think it's good to show how many. Think there's a. I'll just do a simple computation of how many steps are you saving with binary search. So let's say this is just a counter. This is just a while loop. Okay, while you haven't found the middle yet. Worst case scenario, basically this while loop shows that worst case scenario, you find it at the very last end, which is you keep dividing until you find the number, okay, at the very end. So let's say you have an array of, let's say, 500,000, okay? So with the 500,000, how many steps would it take for a binary search? For the linear search, we already know worst case scenario, it would take 500,000. But if you check this one, you save a lot of steps. Only 19 steps for binary search, okay? But again, like what Marvin has told us, this only works if the array is sorted. So you might want to spend some time first, meaning use a sorting algorithm first before using a binary search. Yep. Okay, visualization. Let's go to this one. Okay, I think this is better. Let's do bubble sort. Array size 8, sure, we can run. Let's have a random number. Let's put this, no, some like bigger. Okay. Starting the bubble sort. Let's do one operation. For each pass, we will move left to right. So 0, 7, let's say, and keep swapping adjacent elements, meaning let's 0, 1, 2, 4, as we did. Each pass moves to the next largest element to its final position. This will be shown in green. Okay. Again, it starts as index 0. It becomes light blue. It compares. Am I bigger than you? So index 0 is asking index 1, am I bigger than you? Yes. Let's swap. Okay. Next is I check, am I bigger than you? Yes. Let's swap. Let's swap. Okay. This green denotes that during the what iteration, this part is sorted already. Okay, this one is good. So meaning in the next loop, you don't have to loop 0 to 7. You just need to loop from 0 to 6. Okay, so it decreases as we get to sort some of the elements. So again, you see this as bubbling up, and that's green again. Keep doing that. Oh, this one is, okay. For the third iteration, 126 is bigger than 11, that's why we swap it. But when we evaluate 1 and 2, 158 is bigger, so I don't need to swap, right? Now the pointer changes to 158. So 158 will now do some comparison. Am I bigger than you? No. Okay, maybe I don't need to bubble up. 3 and 4, am I bigger than you? Maybe not, so I'll not bubble up then. 4 and 5, am I bigger? Yes, let's bubble up. And that's sorted. Checks again. Okay, this one is good. This one is good. This one is good. This one is good. So as you can see, even though it's already sorted in our eyes, in the computer's eyes, it still wants to go through the other elements and just keep evaluating. Even though we're not swapping, we're still evaluating adjacent elements. So that's bubble sort. Let's do selection sort. So each pass we will move left to right again and look for the next largest. Once that's found, it will be swapped to its final position. Meaning if I see a maximum number, I would tag it as the maximum number and put it here. So again, at index 0, we tag it as, oh, this is the biggest one we found, okay? It checks for index 1. Oh, index 1 is bigger. So let's tag index 1 as the bigger for now, biggest. And it denotes with the flesh color, okay? And checks, oh, 1 and 2, who's bigger? Okay, 1 is still the biggest. Let's keep that. And they keep evaluating, let's say 1 and 5, which is bigger. It's still 1, the index of 1. And then now, once we reach the end of the array, we can safely say that 993 is the biggest. So we just put them there at the end. So again, we check for the biggest, put them the next biggest, next to the final position. Look for the next biggest, and at 0 comparing to 5, index 0 comparing to index 5. Oh wait, index 5 is the bigger or biggest. So it just, okay, you're good there. I don't need to change anything. Third iteration, or I mean 1, 2, 3, 4, I guess. Evaluates at 4, index 4, swap, and so on. Okay, insertion sort. Okay, what it does for insertion sort, in this case, highlighted green records are, again, it's already sorted. So we begin with record position 0 in the sorted position, and we will keep moving the record in position 1 in blue until it is sorted. So now we can see 0, 1, 2, 3. They're sorted somehow. And then instead of moving them one by one, look what happens here. Okay, when it evaluates with that, that's the time you move it. And then now we say 0 to 4 is partially sorted. And so on. It's a bit similar, okay? Merge sort. You got an array. You select the entire array and then you split it. Okay? You split 0 to 4, 0 to 3, put that here. 0 to 3 becomes 0 to 3. So 2 different arrays. The next step is we keep dividing them. Okay, we keep dividing them until we have an array that has a length of 1 for each. And then now, array of 1 length cannot be split. It's ready for merge. Okay, and they get to be evaluated. Then put them in the right place. Finish merging for that array. Okay, this one we can break it down. And again, sort them. Put them back in the previous array. Oops. So now the next thing is we merge everything together. We compare index 0 and then the other index 0. And the smaller one gets the 0 index. And then also it evaluates for the position 1. And we'll just do the same on the other side. So this is the divide and conquer. Divide the arrays until you can no longer divide them. And now start evaluating and merging them until merge everything together. Evaluate, evaluate. Okay. I think we'll do last the quick sort. Visualize. So you select a pivot and you move it to the end. You partition the subarray and move the left bound to the right until it reaches a value greater than or equal to the pivot. And you keep swapping. And let's just end this. So again, you need to have a pivot and a subarray, and you keep comparing and swapping as all the sorting algorithm, most of the sorting algorithm does. This is swapping elements in place. Don't need to create a new array. Unlike the merge sort, you create a new array. Let's see, do we have a visualized sorting? Let's see, let's put the volume down. I think it has a volume. Okay, as you can see, selection sort, insertion sort is there. Then there's different types of quick sort. This is bubbles. And you can see how fast an algorithm or how many steps it takes for one algorithm over the other. And as you can see, some of them are finishing quite fast already, and the bubble sort haven't even finished yet because it needs to keep evaluating adjacent elements. Even selection sort is taking up a lot of time. Let's see. See if it's better. Okay, same one, but less sort. Left-hand side is the merge sort. So advertisement. Let's see. Shell sort. Okay, I don't know that one. You don't see the linear? Yeah, yeah, because people usually don't really discuss linear so much because by the time you learn the basics of programming, you're doing linear already. And again, this is a sorting, not searching. Let's see if we have search algorithms. Yes, bubble is the longest. Let's see if it has a visualization there. Let's see. Oh boy, oh boy. Seizures, seizures. I hope you guys are just having fun and not really having a fun. If only you can add the music every time it swaps an element or sorts. I'm not your man. You said I'm not your man. Oh, some of the sorts looks very beautiful. Uh-oh. Oh, DJ. What's this sorting? This is merge sort, I think. So this one is beautiful as well. As you can see, it tries to define.
It's like iterative merge sort.
Yeah. I think that's, oh, what's this one? Quicksort. Let's try to switch on radix sort. Okay, I think we had enough of these. And then, let's see. Okay, let's go back to the cheat sheet. So just to give you an idea and give you some numbers. This is a good reference. Other people have printed this one. So let's say you have, let's have an item. Let's say you have boxes, right? You have 16 boxes. And in that 16 boxes, it would take for the log n, let's say it's 0.4 seconds, okay? For all of them, it would take 1.6. Okay? For n log n, it would take 6.4 seconds. For all of n squared, it would take 25.6 seconds. Again, we started with 0.4 seconds. Then come to this factorial. Just for searching in 16 boxes, you would have 66,301 years. Yeah, so you should really try to avoid that. Unless you would be this kind of the developer is like, okay. And then you intentionally make it slow so that when, let's say, either internal or external customer says, hey, can you improve the performance? Then bam, you switch it up. Right? Say, I did improve the performance by 100%. See, that's how you pick your customers or employers.
This is why we can code review.
Yeah. Okay, and then let's see, what else do we have? So let's try the other one. Let's say you have 1,000 boxes. Let's go again to reinforce. If you have 1,000 boxes, the time it takes to log in is 1 second. And for all of them, it takes 1.7 minutes. And log in, it already takes 17 minutes. ON squared for 1,000 boxes will take 1.2 days. And factorial will take 5.4 times 10 raised to 2,638 years. I think the likelihood of a meteor coming here is way higher. Yeah. Let's see, the more important stuff that we have. So another way to visualize actually the linear search and the binary search is, let's say you have a paper. Okay, you have a paper. And then let's say your kindergarten teacher says, oh, can you put boxes with a size of 1 by 1? So you keep doing that until you fill up all the paper with boxes, right? So that takes n amount of time. But if your teacher gave you another kindergarten activity, hey, can you fold the paper until the smallest one you can make? The fact that you fold it one time, I can fold this actually. You fold it one time, that's divided by 2, divided by 2, divided by 2, divided by 2. Okay, and just to give a reference for that one, let's say you have a number guessing game that you created, fun, 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 okay? For a simple search, let's say you have 100 items. The worst case scenario, you take 100 guesses. Binary search for, let's say, 100 items, you just take 7 guesses. Worst case scenario. Big savings, okay? So if you have 4 million items, you take 4 million guesses. And if in binary search, if you have 4 million items, you just do 32 guesses at the most. Okay? And again, that's why simple search has a runtime of O of n. Okay? N being the length of the array, or the number of elements. And then binary search is log n. Again, reverse of exponent. Think of it like a square root, but not so much. Okay? What else can we talk about? Let's see. I think that should be it. Let's see if some muddiest points are good, or I can, let's see. Okay, I can, huh? Yeah, sure. So I can show you code. I don't even need to run it. I'll just show code and I won't run it. Okay, let's see. So let's go with linear search. Don't mind the squiggly because it's TypeScript. Simple for loop. Return I, which is the index. Give you 15 seconds to look at it. Okay. Binary search. Ooh. Take note of this one. Find the middle of the array. And these things are important. If item is less than array mid, search at the other side. This one as well. And as you can see, you update the mid. Okay? So let's say you have 0 to 10. And let's say you did not find it, but you know it's on the left side. Your mid would be, okay, let's say you have your left and you have your right. Your left value is 0, your right value is 10. You search in the middle, which is index 5, you did not see it. Now what should happen is, but you know that, let's say it's on the left side because it's a smaller element. So the right value should become the mid first. So left value is 0, right value is 5, and then check the middle, which is right divided by 2. Let's say 2. Now you keep doing that. Okay? Okay, so basically, let's say you want to do, you have an array of elements. You're looking for the number 45, right? The first thing that the binary search would do, it would search in the middle of the array. And again, this is sorted. So when it first checks the middle of the array, it sees, let's say, 55. 55 is greater than 45, right? So your algorithm, it would already know that, okay, I don't need to search for 55 and at the end of the array, because I know that's sorted and that's 55 and higher. So now I would look at 55 and lower, which is the left side. Oh, okay. We're middle not clearly defined. Oh, so it's up to you. You can do some for division so that you don't take the remainder and just get 2 instead of 3, right? Floor division just helps you with not having a remainder when you do a division in your programming. Some of the programming languages just put, instead of 1 slash to divide, you do 2 slashes. Next, bubble sort. Just need to focus on this one. This one. So if the current one is less than the next one, keep swapping them. Actually, if the other one is bigger, keep swapping them. Okay. The important part here is swapping and having a temporary variable to store that variable that we want to change. Okay. Bubble sort, remember, you need to swap things. So even though, let's say you forgot how to program, when someone says pseudocode it, you just know that you should have a for loop. You want to have something that evaluates 2 positions and you swap. Swap. That's the important part. You swap. Selection sort, insertion sort, we can skip that. Even quicksort. Merge sort is interesting. Let's see. It's way longer because the way we do merge sort is also recursion. We keep, it's like factorial, right? We keep dividing them and then it still doesn't resolve until you compare and then merge, 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 and now it resolves. Kind of like the Fibonacci numbers or factorial, you keep invoking the function until you reach the base case. In this case, your base case is once the array length, an array length is 1, now you can start merging. You can start resolving your recursion. Okay, let's see modiest point. Modiest point. Searching and hash table are interesting, and I'm looking forward to learn about it. Hash table, I think that's for tomorrow. And basically, hash table is a data structure that you can put key value elements. There's a lot of different things it's called, and they have some minimal difference. Hash tables, hash maps, dictionary, even objects. Okay. So hash table, what's good with that is underneath the hood, the algorithm is fast in such a way that if you want to access something, it's O of 1. It's constant. It's very fast. Let's see. Sorting algorithm, time complexity comparison. Okay, I can just show this quickly because the color is really good. So again, when you're comparing stuff, let's go sorting. Just focus on 2 stuff for now: time complexity and worst. Space complexity and worst. So right now, what we taught you is like all of the time, merge sort is somehow generally good. Okay, not the best, but generally good because of the divide and conquer. Bubble sort, not good. And other sorts are complicated. Okay, even in coding interviews, we don't really focus on other types of sorts so much. Okay, and then space complexity. How was it?
It was just, I was like, yeah, I can do merge sort. He's like, yeah, but I'm pretty sure we can do better than merge sort.
Oh no.
Yeah. That means there's something really specific about what's happening.
Yeah. So again, developers usually really study this stuff. These are the things that they also whiteboard, like solving problems and choosing an algorithm. And again, if you don't have an algorithm in mind, let's say you're asked to solve something, it's called brute forcing it. Okay? And brute forcing is kind of like the linear search. Just go through everything and hope that at least you have a result to tell your interviewers that, oh, I solved the problem. It's not efficient. Instead of like trying to do some crazy sorts and then oh, I don't have a result, and then time's up. Okay, it's better to solve it and then keep talking and refactor your code. And usually the interviewer, if they are good, meaning they would guide you. They'll not let you just do it on your own. Yeah. Okay, I think that's, I have a linked list data structure, but that's for tomorrow. Basically, it's just pointing to the other person. Okay, let's say if you want to know someone's address, let's say you point to this person, because this person knows it. Okay, and we'll talk about that more, I guess, tomorrow. That's for today. Let's have a quick break and concept test. And hope you guys can catch up with all the materials. Okay, thank you.